Welcome to Basic Chemistry. Today I am discussing Plus 1 Chemistry, Unit 10, the S block elements. So these elements hydrogen, lithium, sodium, potassium, rubidium, cesium and francium, beryllium, magnesium, calcium, strontium, barium and radium. These elements are known as S block elements. Why these elements are known as S block elements? In S block elements, the last electron enters the outermost s orbitals. It includes elements of group 1 and 2 and helium in group 18. Helium in group 18 is considered as an S block element. That's because the subshell electronic configuration of helium is 1s2 because it contains 2 electrons only. So that means the last electron enters the outermost s orbitals. Okay, that's why includes helium also. And it consisting of 6 elements: lithium, sodium, potassium, rubidium, cesium and francium, not hydrogen. These are called alkali metals. This is lithium, sodium, potassium, rubidium, cesium and francium. Except hydrogen, these are known as alkali metals because they react with water to form soluble hydroxides which are strong base or alkalis. The group 2 includes beryllium, magnesium, calcium, strontium, barium and radium. The group 2 includes beryllium, magnesium, calcium, strontium, barium and radium. These elements, with the exception of beryllium, are commonly known as alkaline earth metals. Why these known as alkaline earth metals? Because their oxides are found in earth crust. That's why these are known as alkaline earth metals. The general outer electronic configuration of S block elements is Ns1 or Ns2. Ns1 is considered as alkali metals, whereas Ns2 is alkaline earth metals. See, these are the electronic configuration of alkali metals. Lithium, atomic number of lithium is 3. So, the electronic configuration is 2s2 and 1s2, 2s1. Okay, the sodium is atomic number is 11. That means the electronic configuration we can write it as 1s2, 2s2, 2p6, 3s1. And potassium is 19. So we can represent it as 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. And rubidium, cesium, francium, etc. The last electron enters in the s subshell or s orbital. That means in these cases lithium is 2s1 and sodium is 3s1 and potassium 4s1 and rubidium is 5s1. Rubidium is 5s1 and cesium is 6s1 and francium is 7s1. So last electron enters in the s orbital. Okay, and it has a very common properties, that is the last electron is only one electron. Okay, that is in the alkali metals the common electrons. Then next, the second group elements, alkaline earth metals. So in beryllium, atomic number is 4, so that is the electronic configuration is 1s2, 2s2. And magnesium atomic number is 12, that is 1s2, 2s2, 2p6, 3s2. Then calcium, that means last electron enter in the 4s2 and strontium 5s2, barium is 6s2 and radium is 7s2. So the last electron enter in the s orbitals. So it is considered as an S block elements. So in this outermost electrons of alkaline earth metal is only 2 electrons. 2 electrons only. Then diagonal relationships. What is diagonal relationship? The similarities in properties shown by diagonally placed elements of second and third periods in modern periodic table is called diagonal relationship. The similarities in properties shown by diagonally placed elements of second and third periods in modern periodic table is called diagonal relationship. So lithium shows similarities to magnesium. Lithium shows similarities with magnesium. That is, lithium is diagonally related to magnesium. So that's why they have some similarities. They have some similarities in their some properties. Okay. So similarly, beryllium shows similarities with the other group elements, that is aluminum. So in anomalous behavior of the first member of a group in alkali metals, lithium shows anomalous behavior and also beryllium also shows anomalous behavior because these are have a very small size and high ionization energy and also high electronegativity, absence of vacant d orbitals. Okay. Next, so we discussing more about a group of 1 elements, that is alkali metals, lithium, sodium, potassium, rubidium, cesium and francium. Atomic and physical properties. So first one, we are discussing electronic configuration. The general electronic configuration of alkali metals may be represented as noble gases, put in a bracket, then NS1. You know, the electronic configuration of alkali metals. You know, 1s2, 2s2 in case of lithium. So, you know, 1s2 means it is a helium, is a helium electronic configuration. So, we can write instead of 1s2, you can write helium, put a square bracket, then you can write 2s1. Similarly, sodium is 11 electrons, 1s2, 2s2, 2p6, 3s1. So, instead of 1s2, 2s2, 2p6, we can write the near the electronic configuration of noble gases, that is 2p6, up to 2p6, that is means 10 electrons. So, you know, neon is a 10 electron, so we can write the noble gas 10, that is neon, square bracket, we can write a square bracket neon, and after that 3s1. Then potassium, similarly potassium is before the element, that is noble gases, is argon. So, that is 1s2, 2s2, 2p6, 3s2, 3p6 means argon electronic configuration. So, argon is atomic number is 18. So, up to 3p6, that is 18 electronic configuration. So, we can write the noble gases argon. So, put the square bracket argon, after that you can write 4s1. That is only the rubidium, cesium and francium you can write. Okay, that's a general electronic configuration of alkali metals using the noble gas configuration. Okay, right. Then atomic and ionic radii. The alkali metals have largest size in a particular period of the periodic table. Okay, alkali metals have largest size in a particular period of the periodic table. So, with the increase in atomic number, the atom becomes larger. Increasing atomic number, the atom becomes larger because size will be increases. The monovalent ion M plus are smaller than that of the parent atom. Like example is sodium. Na plus is because of the 1 electron losses, sodium atom is converted into Na plus ions. That is Na plus ions means 1 electron losses. So that is Na plus means it has only 10 electrons, whereas Na is 11 electrons. So, you know that is Na plus will be smaller than that of Na, that is 10 electron will be smaller than that of the 11 electron. So, we can write monovalent ion M plus are smaller than that of the parent atom M. Okay, right? The atomic and ionic radii of alkali metals increases on moving down the group. Both atomic radii and the ionic radii of alkali metals increase on moving down the group. Okay. Then ionization energy. We already discussed ionization energy increases left to right, whereas top to bottom ionization energy decreases. What is ionization energy? Ionization energy is the energy required or the minimum energy required to remove an electron from an outermost shell of an isolated gaseous atom. Okay. So, the alkali metals have a low ionization energies. Okay. Their atomic sizes are quite large. The valence electrons are quite loosely held by the nucleus. So, on moving down the group, the ionization energy decreases. It is due to the increase in size of the atoms. Okay. So, in increasing the magnitude of the screening effect caused by the increase in the number of intervening electrons, that is inner electrons. Okay. Screening effect also increases, then ionization energy also decreases, right? The next, hydration enthalpy. The hydration enthalpy of alkali metals decreases with the increase in size. Hydration enthalpy of alkali metals decreases with the increase in sizes. The smaller the ion, the more is the extent of hydration, because the smaller the ions means in lithium forms Li plus ion, Na forms Na plus ions, potassium K plus ions, rubidium Rb plus and cesium Cs plus ions. So, these ions have a high size will be in case of cesium ions. Okay. Then lithium ions Li plus will be the smaller ions. So, smaller ion can form more the extent of hydration. So, that is due to this in aqueous solution, the hydration enthalpy decreases in the order lithium greater than lithium plus, that is ions. In case of ions, lithium plus is greater than Na plus, greater than K plus, greater than Rb plus, greater than Cs plus. So lithium have high hydration enthalpy because of smaller the size. Okay, it can form more extent of hydration. So in hydration enthalpies of alkali metals ions decreases with the increase in ionic sizes. So alkali metals decreases, hydration enthalpy of alkali metals ions decreases with the increasing ionic sizes. So cesium plus ion has a low hydration enthalpy, whereas Li plus ion has more hydration enthalpies. Okay, right? Then physical properties of alkali metals. So what are the physical properties? Metallic character. All the alkali metals are silvery white, soft and light metals. Okay, the metallic character increases down the group. So metals are metal losses electrons. So in alkali metals are electropositive metals. So the metallic character increases down the group. The density, because of the larger size, alkali metals have a low density. Because of the larger size, alkali metals have a low density. The density generally increases the down the group. Increases down the group. Both the metallic character and the density also increases down the group. Right? Then melting and boiling points. The melting and the boiling points of alkali metals are low. Melting and the boiling point of alkali metals are low. It indicates weak metallic bonding due to the presence of only a single valence electron in them. That is a single valence electron. So that is loosely bonded single valence electrons in them. The melting and boiling point decreases down the group. Melting and boiling point decreases down the group. Okay, right? Then when alkali metals or their salts are heated in the flame of a Bunsen burner, they impart characteristic color to the flame. That is, lithium shows crimson red and sodium golden yellow, potassium pale violet, rubidium reddish violet and cesium sky blue. So these are the color shows alkali metals, right? Then alkali metals have a low ionization energy. We already discussed, and therefore the electron present in their atoms. So that is, alkali metals have a low ionization energy. Therefore the electron present in their atoms get readily excited because there is no bonded, there is no attraction with the nucleus and the outermost electron. That is loosely bonded electrons. Last electrons are loosely bonded because low ionization energies. So the electron present in their atoms get readily excited to higher energy states by absorbing energy from the visible region of the light. Okay, when these electrons jump back to the ground state, they emit energy in the form of radiations. So these radiations fall in the visible region, imparting characteristic coloration to the flame. That is why we can see the lithium, sodium, potassium, rubidium, cesium shows these characteristic colors to the flame. Okay, lithium shows crimson red and sodium golden yellow, potassium pale violet, rubidium reddish violet, cesium sky blue. That's why, because these free electrons, the freely bounded electron or the electron present in their atoms get readily excited to higher energy state by absorbing energy from the visible region of the light. When these electrons jump back to their ground state, they emit energy in the form of radiation, and these radiation fall in the visible region, imparting characteristic coloration to the flame. That's why we can see the color of the alkali metals, right? Thank you.